In this video, we're going to discuss Chapter 5 revision quiz. So we have handpicked over here about 18 questions to be discussed one by one. So let's start with question 1 over here. So X and Y are two solenoids arranged coaxially. So when we say coaxially means by solenoid X and solenoid Y, they share the same axis. They co means share, axial means axis. So share the axis. So you can see coil X and coil Y, they share the same axis. Okay, so X carries a constant current I as shown in the figure and moves with a constant speed away from Y. So you can see in this diagram over here, there's current flowing in solenoid X because you place a battery over here to provide a steady current flowing in solenoid X. So now solenoid X will be moving with a constant speed away from Y. So it will be getting further and further away from Y. Okay, as a result of electromagnetic induction, an induced current flow in the straight wire Mn. So the idea is like this: when we shift this solenoid X away from solenoid Y, the magnetic field that is passing through solenoid Y will decrease. So it will cause a decrease in the magnetic flux. So when there's a change in magnetic flux, there will be an induced EMF. So since this is a closed circuit, the induced EMF will induce a current flow inside this solenoid. So there will be current passing through this straight wire Mn over here. And there is a force between X and Y. Okay, so we should expect that this current flowing in this solenoid Y here will produce a magnetic field as well. So because solenoid X will produce a magnetic field, solenoid Y will produce a magnetic field. So their magnetic field will cause a magnetic force between coil X and coil Y. So there will be a magnetic force also. So which of the following is correct? So they will be asking whether the current is flowing from N to M or M to N. And they ask whether the force between X and Y is an attraction force or repulsion force. So let's go through this situation right now. Okay, so we know that the how it works is should be like this. Okay, solenoid X moving away from solenoid Y. Okay, so this motion here is going to cause a decrease in magnetic field, passing decrease. Decrease in magnetic field produced by solenoid X passing through solenoid Y. Okay, so because there's a change in the magnetic field that is passing through solenoid Y, there will be, in this case, it will be a decrease in the magnetic flux. Decrease in magnetic flux for solenoid Y. And because solenoid Y experience a change in magnetic flux, therefore you should expect there is an induced current. Induced EMF first. Induced EMF in solenoid Y. And because solenoid Y here it's a closed circuit, okay, means by it's a closed loop, therefore you have induced current in solenoid Y. And the induced current in solenoid Y will create a magnetic field. Okay, the induced current is the one that will create a magnetic field. Magnetic field ni, we call it By, okay? Magnetic field produced by coil Y. So magnetic field By created by induced current in solenoid Y. Okay, so these two magnetic field will interact. Okay, coil X will interact with the magnetic field produced by coil Y. Okay, solenoid X will interact with the magnetic field produced by solenoid Y. Solenoid Y will interact with the magnetic field that is created by solenoid X, and as a result, both of them will experience a magnetic force. Okay, solenoid X and solenoid Y experience magnetic force. Okay, solenoid X experience a force because solenoid X interact with the magnetic field produced by solenoid Y. Solenoid Y experience a magnetic force because solenoid Y interact with the magnetic field that is produced by solenoid X. That's why both of them experience a force, and we need to determine whether it's an attraction force or a repulsion force. Okay, so I'll go through the more direct way of determining the direction, which is using our right hand grip rule. Okay, so from using our right hand grip rule, if we grip, if this is our rod, then we have our solenoid. We can see that for coil X, the current is flowing upwards in front of the rod. It's flowing downwards behind the rod. Okay, if you want to draw it, maybe behind the rod is going downwards. Okay, so your fingers will be going upwards in front of the rod, and your fingers will be going downwards behind the rod. Upwards in front of the rod, downwards behind the rod. Okay, so in that case, your thumb will be pointing to the left. And because your thumb is pointing to the left, that means your left hand side will be the north pole, your right hand side will be the south pole. Okay, when we say north south, what does it mean is when you draw your magnetic field, right? Your magnetic field will be coming out from the north pole, it will be coming into the south pole. So your magnetic field lines will be pointing from right to left. Okay, that's the idea when we say the north pole is on the left, the south pole is on the right. Okay, so now this solenoid X here, it's moving away from solenoid Y with a constant speed. And because it's moving away, right, then it will cause these things happening here. At the end, you induce a current over here. Okay, so based on Lenz's law, right, we know that this induced current, right, will be in the direction that will oppose the change in magnetic flux that happens here. Okay, so that means by this induced current over here will be in the direction to oppose the decrease in the magnetic flux. Or in other words, this induced current here will try to increase the magnetic flux for solenoid Y. So if we want to increase the magnetic flux for solenoid Y, means by we want to pull this coil X back towards coil Y. Okay, again, there's magnetic field passing through coil Y, and that magnetic field is produced by coil X. Okay, now magnetic field, what should I say? Okay, so this induced current here will try to oppose the change in magnetic flux, and right now the change is a decrease in magnetic flux. So our induced current here will try to oppose the decrease in magnetic flux. The decrease in magnetic flux is caused by this solenoid X moving away. So this induced current here will try to oppose solenoid X from moving away. So if the induced current want to oppose solenoid X from moving away, the induced current here will need to try to attract solenoid X towards solenoid Y. Okay, the thing is moving away. You want to oppose it from moving away. That means you want to pull it towards you. So if you want to pull it towards you, then the force between X and Y should be an attraction. Because you want to oppose it from moving away, that means you want to pull it towards. Pull it towards you means by it's an attraction. So from there, we can remove repulsion from a picture. Attraction is correct. Okay, so if we want to attract, we know that, okay, let's keep the diagram a bit simpler. Removed all the magnetic field lines. We know that north pole is on the left hand side and south pole is on the right hand side of solenoid X. So if you want to attract, right, we know that opposite pole should attract. That means when we want to create a north pole over here for solenoid Y, our south pole should be over here. Okay, if our north pole is over here, our south pole is over here, then it will cause an attraction between these two solenoid over here. Why? Because this is S, this is N, this is opposite pole. Then they will attract each other. So this is an attraction. This is what we want to achieve. Okay? If you want a repulsion, then you have to create the south pole to be over here. Then it will be like pole. Then it will cause a repulsion. Okay, but in this case, attraction is what we want. We want to oppose solenoid X from moving away from solenoid Y. So we want an attraction. That's why what we need here, it's a north pole on the left of solenoid Y, south pole on the right of solenoid Y. This is what we want. Okay, so when we want to determine back the direction of the induced current, we know that our induced magnetic field will need to be like this. But how do we deduce the direction of the induced current from the induced magnetic field? We know that the magnetic field for solenoid Y will have its north pole pointing towards the left. Okay, so if our north pole is pointing towards the left, we see that our fingers is pointing upwards in front of the rod, pointing downwards at the back of the rod. Okay, upwards in front of the rod, downwards behind the rod. Okay, you should see it from this angle. Okay, if you want your north pole to be pointing to the left, then you'll be up in front, down, back. Okay, I'm not sure whether the camera is flipped or not. You have to use your hand to determine it. So in front of the rod is what we can see here. That means by up here, the current should be all pointing upwards. Okay, again, it's up, down. Okay, pointing to the left, up, down. So your current should be all pointing upwards in front. At the back, it should be pointing backward, downwards. Okay, so if you trace out this circle over here, then you know that this is down, then you see that the current flows like this. Okay, therefore you can see that the current flows from N to M, and therefore our answer is A over here. Okay, you have to look at whether it's up in front of the rod or back or down in front of the rod, whether it's down at the back of the rod or up at the back of the rod. So from there you can determine how the current flow at the solenoid. So by looking at how the wire is being wound, you can continue to draw the arrow for current to determine the current flowing through the straight wire. Okay, if I want to highlight it, you can think of it like moving up, 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 down, down, to the left, up, up. So you can see the whole circuit, how it works, and from there you can determine the current is flowing from N to M. That's why the answer is A. Okay, then so there are many ways to interpret it, but always the central idea is that you want to oppose the change in magnetic flux. The change in magnetic flux here is caused by this solenoid X moving away, so you want to oppose it from moving away. That's why you want to attract it towards itself. That's why it's an attraction. So because you will know it's an attraction, we know that here should be a south pole, here should be a north pole, here should be a south pole. So from this, we can deduce the direction of the current flowing in the solenoid. And from there, we can deduce the current flowing through the straight wire MN. So this is how I solve question 1. Question 3. An aluminium ring hangs vertically from... zoom in first. Question 3. An aluminium ring hangs vertically from a thread. So this is a thread over here. Then you have a ring hanging. You have a ring hanging at the bottom of the thread. So if a solenoid is fixed near the ring and coaxial with it. So this is a solenoid and it shares the same axis with the ring over here. That's why I call it coaxial. They share the same axis with the ring. Okay, so what is the initial motion of the aluminium ring when the current in the coil is switched on? Okay, so what happened is they are going to switch on the circuit by closing the switch over here. So when they close the switch, then you know that current will be flowing from the positive terminal to the negative terminal. So you up, down, 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 down, up, up, up. So you know this is how the current will flow when you close the switch over here. Now they ask, when you close the switch, what will be the initial motion of the aluminum ring. Okay, the idea is like this. If you close the switch, initially, okay, let's write it down. Initially, before you close the switch, there should be no current. Yeah, what am I writing? Initially, I initial should be equals to 0, but final, when it reaches a stable value, I will be equals to I max or I steady. Okay, so it takes some time for you to reach the final value of current, from 0 to the final value of current. Okay, but it's an increase in current. Okay. Okay, so when there's an increase in current, that increase in current is going to cause an increase in the magnetic field produced by the solenoid. Okay, increase in the magnetic field produced by a solenoid. What is the direction of the magnetic field produced by a solenoid? You can determine it using a right-hand grip rule. I can determine it by myself, you determine it by yourself, but using your right-hand grip rule, you'll see that your thumb will be pointing to the left. Okay, the thumb will be pointing to the left. That means by here should be the North Pole, here should be the South Pole, and your magnetic field lines will look something like this. Okay, so it'll be pointing out from here, be pointing into here. Okay, so you see that there will be magnetic field lines passing through the ring because there's the ring is near the solenoid. That's why there's magnetic field lines passing through the ring. Okay, and since this is an increase in the magnetic field, then it will cause an increase in the magnetic flux passing through the ring. Increase in magnetic flux passing through the ring. I shouldn't write passing through. It's the magnetic field that passes through the ring. It's increased in magnetic flux of the ring. Okay, so because there is change in magnetic flux, it will cause an induced EMF. And since this is a closed circuit, then it will cause an induced current. Okay, so induced current here, because there's current flowing in the ring, here in the ring, everything here is in the ring. Because there's induced current in the ring, there will be magnetic field produced by the ring. Okay, so I will represent it in green, so probably the magnetic field should look something like this as well, but we don't know the direction. Okay, but we know that this magnetic field produced by the ring will interact with the solenoid. Okay, means by the solenoid will interact with the magnetic field produced by the ring. That's why the solenoid will experience a force. At the same time, the ring will interact with the magnetic field produced by the solenoid, and the ring will experience a magnetic force as well. Okay, because there are magnetic field produced by the coil, there's magnetic field produced by the ring. The coil will interact with the magnetic field produced by the ring will interact with the magnetic field produced by the coil. So because they interact with the magnetic field, then they will both experience a magnetic force. So they'll either push away from each other or they'll pull towards each other. Okay, that's the idea. Okay, so what I want to mention here is that all these things here, induced EMF, induced current, magnetic field induced at the ring, and the magnetic force experienced, all these things are induced, okay, or we can call it as they are electromagnetic induction effect. Okay, they are the effect of electromagnetic induction. Okay, so this part over here, this part over here, you can call it as the cause of the effect. Okay, what causes this induced EMF, induced current, induced magnetic field, induced magnetic force? All these things are induced, but what is the cause? It's caused by the increase in current in the coil, causing the increase in magnetic field produced by the solenoid, causing the increase in magnetic flux of the ring. This is the cause, this is the effect. Okay, so if you refer to Lenz's law, right, Lenz's law say that the direction of the electromagnetic induction effect will be in a direction such that to oppose the cause of the effect. So the magnetic force will be in the direction to oppose the cause of the effect. The magnetic field will be in a direction to oppose the cause of the effect. The induced current will be in a direction that try to oppose the cause of the effect. The induced EMF will be in the direction that oppose the cause of the effect. Okay, so the cause of the effect here is the increase in current. So this magnetic force or magnetic field here, or induced current or induced EMF here, you try to oppose the increase in current, or you try to oppose the increase in magnetic field. Okay, so in this case, it's more appropriate to say that the magnetic force will be in the direction to oppose the increase in the magnetic field. So there's an increase in magnetic field passing through the ring over here, and now the magnetic force here will try to oppose the increase in the magnetic field. So how do you reduce the magnetic field that is passing through the solenoid? Passing through the ring. How do you reduce the magnetic field that is passing through the ring? By getting away from the coil. By getting away from the coil, you are able to reduce the magnetic field that is passing through the ring. Okay, so it will try to oppose the increase in magnetic flux. That's why you try to move away from the coil. Okay, let me try to probably make it nicer. How to explain it nicer? Magnetic force will be in the direction to oppose the increase in the magnetic field. Okay, so right now the situation is, if you look from this angle, you see that the ring is like this. Then for this situation here, there are magnetic field. This is the ring. This is the magnetic field of the solenoid. And it's increasing due to increase in current. This is the situation right now. And right now, our magnetic force will want to oppose this. Okay. Magnetic force want to oppose the increasing B. Okay, if you want to oppose the increasing B, means by you want to reduce the B, right? If you want to reduce the B, the best way to reduce the B is to get away from a solenoid. If you get away from a solenoid, the magnetic field that is experienced, the magnetic field produced by the solenoid will not be that strong if you're further away from a solenoid. That means you are in an effort to reduce the magnetic field passing through the ring. Okay, so that's why you want to move away from the coil, because you want to try to oppose the increase in magnetic field by trying to reduce the magnetic field passing through the ring. Okay, it's the magnetic field produced by a solenoid, but it's passing through the ring. Okay, so I hope it's clear enough. Yeah, if you still have any question, feel free to ask me again. Okay, I don't think I did a very good job in explaining this one. Okay, next one. The figure below shows a circular coil with its plane perpendicular to a uniform magnetic field of flux density B. So when you say magnetic field of flux density B, right, that means the magnetic flux density is B. Magnetic flux density is magnetic field strength. Okay, so you can change the sentence to be the figure below shows a circular coil with its plane perpendicular to a uniform magnetic field of strength B. Okay, so this is the magnetic field. These crosses here are magnetic field, and this circular coil here has a plane which is on the plane of the screen, and your magnetic field is pointing into the page, so it's perpendicular. Okay, the plane of the coil is perpendicular to the magnetic field. Plane is like this. Your magnetic field is pointing into the page, so it's 90 degrees. Okay. The magnetic flux density B varies with time as shown in the figure below. So you can see that the magnetic field initially increases, and after that it remains constant, then it decreases. Okay, so you know that the change in magnetic field here is going to cause a change in magnetic flux through of the coil. Okay, if you change the magnetic field passing through the coil, then you're going to change the magnetic flux of the coil. So the change in magnetic flux is going to induce an EMF. Okay, which of the following shows the variation of the magnitude of the EMF induced epsilon with time? So now they are asking, how would the graph of epsilon against time looks like if our magnetic field is changing like this? Okay, so I hope this one you need to, how should I say it? You need to refer to the idea of Faraday's law. Okay, Faraday's law will be helpful here. Okay, Faraday's law tells you that the induced EMF will be negative of the change in the magnetic flux linkage with time. Okay, or in other words, you can break it open, then it become the change in magnetic flux, the time rate of change of magnetic flux. Okay, so you can see that you can further open it. Okay, then this will be the BA cos theta. This is just magnetic flux. In this situation here, you are changing a magnetic field. You are not changing the area. You are not changing the rotation, the orientation. So this thing will be constant because you are not changing the area. This thing will be constant because you are not rotating the coil. So you can take it out from the differentiation bracket. So it becomes NA cos theta. So what's left? What's changing here? It's B. So you have to leave it in the differentiation bracket. So this will be dB dt. Okay, I'm showing you here how to derive the equation here. But here's what you can see. If your dB dt is positive, then the positive here will multiply, will multiply with the negative here, then you get a negative answer for epsilon. Okay, epsilon will be negative. Continue. If your dB dt is negative, then if this is a negative value, then negative multiply with the negative here, you get a positive epsilon. This is the idea that we'll be following here. But dB dt over here will be represented by the gradient of BT graph. And we have BT graph over here that is going to tell us about the gradient of BT graph is going to tell us about the dB dt. Okay, so let's look at we split this graph over here into 3 sections. First is a section from 0 second to 4 second. The second section will be from 4th to 6th second. The third section will be from the 6th second to the 8th second. So there's 1 section, 2 section, 3 section over here. So in the first section, you can see that it's a linear increment of magnetic field. So throughout the process, I believe you can see that the gradient is constant. The B is increasing, but the dB dt is not increasing. The dB dt is constant, okay? Because the gradient is constant. Okay, if the if dB/dt increasing, then that means it's going higher and higher like this. But that is not the case over here. Over here, the gradient is constant. So we can see that we can make a conclusion. It's a positive gradient, so you know dB/dt is positive. And you know dB/dt, it's constant because the gradient is not increasing, it's not decreasing. The gradient is remaining constant. You're not increasing a gradient, you're not decreasing a gradient. Okay, that's the first section. So this will tell you that the EMF is negative. This will tell that the EMF is constant. Okay, so this is what you know from the first section. But if you look at the diagram over here, you can see that there is no negative EMF here. Why there's no negative EMF here? Because if you read the question, they say shows the variation of the magnitude of the EMF induced. That means they are only concerned with the value without concerning the sign for the EMF. Okay, so what you need to do is just to know that the EMF is constant and there is an EMF and it's not zero and it's constant. Okay, that's what you need to know here. So because you see that EMF is constant from 0 to 4, that means you should expect a horizontal line from 0 to 4. Right now, if you look at this EMF here is increasing. It is not constant. Okay, so this one is not the correct answer because the EMF is not constant. This one, the EMF is also not constant. It is decreasing. So A and B can be eliminated from our selection. Okay, so let's continue. For the second section, we can see that the gradient is not changing again, but this time the gradient is equal to 0 because it's flat. The gradient is flat. That's why you can make a conclusion that dB/dt is 0 and dB/dt is constant at 0. So this one will tell you that the epsilon will be equal to 0 and epsilon is constant. Okay, so both of the epsilon here, both of the EMF here is equal to 0 from 4 to 6 seconds. So both of these are still in the race. Both of these are still probable valid answer. Okay, next we continue. We'll continue the third section. The third section consists of constant gradient as well, but this time the gradient is a negative gradient. Negative constant gradient. So dB/dt over here it's negative. And dB/dt here is constant. So what do we know? We can say that the epsilon will be positive. Then we also know that the epsilon is constant. Okay, so both of these are constant EMF. They are not increasing, they are not decreasing, and they are positive. We don't care about the sign anymore. Okay, but both of these is still in the race. But what's the difference between the graph in C and the graph in D right now is you can see that graph C has a higher EMF, a greater EMF for the later section, whereas for graph D, you have a greater EMF for the earlier section. Okay, so we know that from this equation, we know that if our dB/dt has a larger value, if dB/dt has a larger absolute value, then our modulus of EMF will be larger. Okay, if you don't want to care about the direction, what we can do is we can put modulus around it. So we don't need to put a negative sign because we want everything to be positive. So this cos theta here technically becomes 0. In this case, it becomes 0. Not 0, it becomes 1. Theta will become 0, cos theta will become 1. Okay, the dB/dt here, we should put a modulus around it because dB/dt can be increasing, can be decreasing, and we don't want to care about it. So if we write it like this, then we know that this thing should always be positive, this thing should always be positive, this thing modulus already become positive, this thing modulus already become positive. So this is another way of writing it if you don't want to care about the direction. Okay, so for now we know that dB/dt larger will cause your magnitude of induced EMF to be larger. And dB/dt larger means by steeper gradient. Whether it's positive gradient or negative gradient, don't care. If it's steeper, then the DBDT will be larger. Steeper means more churn. Okay, so which one is steeper? Well, you can see, probably logically, you can see that the later section is steeper because it takes 2 seconds to drop from high to low. Whereas this one, it takes 4 seconds to go from low to high. So if it takes longer time to make these changes, then that means it's not so steep lah. If it takes only 2 seconds to make these changes, then that means it's a faster change. It's a steeper gradient. So because the later section here is having a steeper gradient, the later section over here should have a greater modulus of dB/dt. Then therefore, it should have a greater induced EMF. So greater induced EMF should happen at the later section. So from here, we can see that D will not be the correct answer. Okay, therefore our answer is C. Okay, you can say this one has a larger modulus of dB/dt. This one has a smaller modulus of dB/dt. Okay, that's why this one has a smaller magnitude of induced EMF. This one has a larger magnitude of induced EMF. Okay, that's how you arrive at answer C over here. Okay, so that's it for question 5. Let's move on to the next question. Question 6. A straight conductor is moved at right angles across a uniform magnetic field. So the graph below shows x of the conductor from its initial position with time t. Show x of its conductor from its initial position with time t. Where's the x? I think the displacement here probably should change to x. Okay, it's showing the position x of the conductor from its initial position with time t. Okay, the idea is like this. Probably need to draw this out. This one is a bit more complex. You have a uniform magnetic field. I'll express this in terms of these crosses over here. You have magnetic field pointing into the pitch. And you have a straight wire conductor, probably a different color. Okay, so it starts at position here, let's say x equals to 0. Then the straight conductor will be moving. Should probably just draw a line. Okay, and call this moving. Okay, so as it moves, then the x will increase. Okay, so this is what you see here. The x increase, continue to increase, continue to increase, then not increasing anymore. Okay, we can call this as x. Okay, so technically, if we look at this diagram over here, this diagram here is going to tell us how fast is the straight wire conductor moving. If you see that the gradient is very steep, that means it undergoes a very big change in position within a short amount of time. Then that means it's moving very fast. You see a very not so steep gradient like this one probably not so steep. That means it takes a long time to have a bit of change of position. Then that means it's moving very slow. Okay, so from this diagram over here, we can deduce how fast is the straight conductor moving. Okay, we can see from here that this is quite steep. So this is moving quite fast. This is moving relatively slow. And if you can see here, the x never change within this time frame over here. The x never change. It's constant. The x never change, that means it is staying at a certain position, not moving anymore. So this is a position where it's not moving. Okay, fast means by you have a larger v. Slow means by you have a smaller v. Not moving means by your v is equal to 0. Okay, so you know that if you have a straight wire conductor moving at right angles to the uniform magnetic field, then you know that the induced EMF will be equals to B L V sine theta. Okay, the sine theta, occasionally you have see people with sine phi and sine theta. Occasionally you see people just omit the sine theta. It depends on what's the setup that you have. For this setup over here, you can take this one to be equals to 1. Okay, because it's at right angle, so you can just put this to be BLV. Okay, so we know that from this relationship here, we can see that V will be proportional to our epsilon. Okay, our B here is constant. The length of our rod is also constant. That's why we know that the speed of the rod moving will be directly proportional to the EMF. So if we see a larger V, then you should see a larger EMF. If you see a smaller V, you should see a smaller EMF. If you see your V is equal to 0, then that means your epsilon should be equal to 0. So the first tip that we know that will show the most obvious pattern is that V equals 0 will cause, this one is submit 0, your EMF will be 0. So you know that the fourth section here should have EMF of 0. So the only one that fulfills this condition is the graph at D. So ABC will be wrong. Okay, so I want to emphasize, why do you see straight line over here? It's because the gradient is not changing. It's a fast moving straight conductor. It has a large V, but the V is not increasing, the V is not decreasing. The V is a constant V. That's why the V constant, that's why the epsilon is constant. The EMF is constant. Okay, again, want to emphasize, if you look at the gradient is not changing. That means it's a constant V. Okay, if your gradient is changing like this, then this is called increasing V. But that is not the case. Okay, if your V is constant, then you expect your EMF to be constant as well. That's why you see a constant EMF for the first section. You see a constant EMF across the second and third section. Because from the second to the third section, the gradient remains the same throughout the second and third section. That's why the EMF also constant at a certain value throughout the second and third section. Okay, that's why this will be the correct graph. This will be the answer. Okay, so it is based on this equation over here. Okay, so this is how you solve question 6. Let's move on to the next question, question 10. So a short coil is wound over the middle part of a long solenoid as shown in the figure below. So your coil is wrapping around the solenoid near the middle here. Okay, then they say the current in the solenoid varies with time as shown in the figure below. So they are going to supply current, or they are going to introduce a current flowing inside the solenoid, and the current is going to change from 0 to a certain peak, then it will drop back down to 0. Okay, so which graph shows the variation of the induced EMF in the coil with time t? Okay, so if you look at the situation here, there's coil, there's solenoid, there's two current loop over here. So when you see this kind of situation, you know it's a mutual induction situation. Okay, mutual induction. So when you have mutual induction, if it's possible, you would like to determine which one is the primary coil, which one is the secondary coil. So primary coil is the one that we drive a current inside it, we change the current inside it. Okay, the secondary coil will be the one that has an induced EMF in it. There's an induced current in it because of the change of magnetic flux that it experiences. Okay, there will be one primary coil that will be the one that we supply current and we change the current, and the change in current is going to change the magnetic flux passing through another coil, causing an induced EMF in another coil, and the another coil we are going to call it the secondary coil. Okay, so in this case, since current is flowing in the solenoid, as you can read here, then that's why the solenoid is the primary coil, and the induced EMF is in the coil. That's why the coil here is the secondary coil. Okay, so in this situation here, they are interested in the induced EMF in the coil. So they are interested with the secondary one. So that means it's EMF 2. So you know that for mutual induction, EMF 2 will be due to the change in current in 1. Okay, that means by the change in current in 1 is this graph over here. Okay, you can call this as I1 also can, because this is current in the solenoid varies with time. This is just how I1 is going to change with time. So we know that if you are able to differentiate the graph of I1 with time, I1 with time, you differentiate, that means you find the gradient across the whole graph, then you negative it, then you get the answer for epsilon 2, the EMF induced in the secondary coil. So if you look over here, the gradient of this graph flip the sign, then you get the epsilon t graph. Okay, so over here you can see that initially the gradient is 0. So if initially you see a gradient is 0, I should clear this out. When I say initially gradient is 0, because it starts flat, then only slowly increase the gradient. So gradient is equal to 0 initially. So that means at time equals to 0, because your gradient di dt is equal to 0, that's why your epsilon is equal to 0. Okay, so this one fulfill a condition, this one fulfill the condition. It starts out with 0, but this one start at the peak, so this one is wrong. This one also start with 0, so this one's still okay. Okay, until now this is the situation that we have. Then after that, if you look at the situation, it's an increasing gradient, so you should expect the value later to be getting larger and larger. It can be getting larger in a positive way or getting larger in the negative way. This one we have to look at the sign. Okay, right now the gradient is increasing. That means by the di dt is positive because it's a positive gradient and it's increasing. Okay, so because you flip the sign, then you know that epsilon is negative, but the absolute value is increasing in the negative side. Okay, so this one is increasing in the positive side, so this one is wrong. This one is increasing in the negative side, so this one is correct. This one is increasing in the positive side, so this one is wrong. So from here you can determine the answer to be B. Okay, you can continue the process, never mind. Okay, you can continue the process. At some point you see that the gradient decrease to 0, you get flat over here. So the gradient decrease to 0, that means the di dt is still positive, because it's still positive gradient, just that it's getting flatter. Positive gradient, it's not negative gradient, it's positive gradient but getting flatter. So right now di dt is positive but decreasing. So you flip the sign, then it become the epsilon is positive. The epsilon is positive. Wait. The di dt is positive gradient, sorry. It's positive gradient but decreasing. What am I writing? Let me write here. Let me remove everything here to avoid confusion. Okay, initially the di dt is 0, then the epsilon will be 0, then di dt is positive. And increasing. Okay, you can say the di dt is increasing. Therefore, you can see that the epsilon is negative and the absolute value is increasing. Okay, so this is what we see over here. It's negative value for epsilon and the value, the absolute value is increasing over here. This is what we see over here. Then after that, at this region over here, it's decreasing gradient, but it's still positive DIDT. The gradient is still a positive gradient. It's not negative gradient, it's still a positive gradient. That's why you can write DIDT is positive. But you can see it's getting flatter and flatter. That's why the gradient value is decreasing. Okay, so from here we can say epsilon, flip the sign from DIDT, then it becomes negative epsilon. But you know that because DIDT is decreasing, the absolute value is decreasing, the absolute value of EMF will be decreasing. So this is what we see over here. Okay, then you reach this point, which epsilon is equal to 0, is exactly at this point when DIDT is equals to 0. So at this point, DIDT equals to 0, then your epsilon is equals to 0. This is this point over here. Okay, then we continue. Now it's negative gradient, but it's getting steeper and steeper from flat to steep. So right now, DIDT is negative gradient because it's now sloping downwards already. And you know that it's getting steeper and steeper. So this one is DIDT increasing. The absolute value is increasing. So therefore, you can say the EMF, it's a positive EMF, but the magnitude, or you can say the absolute value of it, is increasing. So you can see the value is getting larger and it's positive. Okay, this one is negative, this one is negative. Okay, you can continue after that. You can see that the gradient is decreasing, but it's still negative gradient. This is negative, this is decreasing. So you see that EMF will be positive, but the absolute value of it is decreasing. And this is responding to this one. And come back to 0 because at the end it becomes flat over here. Okay, so it's just analyzing how the gradient, the differentiate the graph, then flip the sign. Then you get the graph for B. And this is how you solve this question 10 over here. Question 12. A coil of n turns, each of area A, is placed in the uniform magnetic field B. Okay, the magnetic flux link with the coil is described by the expression MBA cos theta. So magnetic flux link with the coil. So this one is magnetic flux linkage. So the magnetic flux linkage expression is MBA cos theta. So which angle in the figure below represents theta? Okay, so we need to know what is theta first. Only we can see which diagram here makes sense. So let's try to think about it. So magnetic flux linkage is equals to n times phi. So this one is linkage. If it's capital phi, is linkage. If this one is not linkage, it's just magnetic flux. Okay, so it's for each turn of coil, what's the magnetic flux? This is if you link them together, what is the magnetic flux linkage? Okay, so we know that magnetic flux is a dot product of B and A, which if you open it up, then you become MBA cos theta. Okay, that's the definition of magnetic flux. So therefore, you know that the angle over here will be the angle between A and B, B and A. Okay, so this one is quite straightforward. If you look at the diagram, you know that all the B here is pointing to the right. That one is very straightforward. So it's straight away forward. Okay, so next we continue to the area vector. The area vector must always be perpendicular to the plane of the coil. Okay, so we can see here our coil is oriented in this slanted way. So normal is the word perpendicular. So you know that our area vector will either be pointing in this direction, or the area vector will be pointing in the opposite direction of this arrow over here. Normal, there's one side, there's this direction of normal, and there's the opposite side of normal. Okay, of course you can draw your normal to be here also, right? Not the best way of drawing. You can draw your normal to be pointing here as well. This is also normal, of course. So your area vector, you can assign it to be here. You can also assign it to be here. Okay, if you assign it to be here, then the angle will be angle between A and B will be this theta over here. Okay, but if you assign your angle to be not here but here, then A and B, the angle between them will be here. Okay, so which one will be more appropriate? Well, we can see that this angle over here is equal to the angle over here. So actually this will be our answer. Okay, if you look over here, this will be the area vector, or this will be the area vector, one of it. Okay, we can see that this angle over here is definitely not equal to that angle over there. So not this one. So this one, this will either be the area vector, or this one can be the area vector as well. This is the angle. So the theta over here, should be 90 minus this theta over here. Only you get answer. 90 degree is over here. This is 90 degree. So take 90 degree minus the angle that they label over here. Only you can get the angle between B and A. So this one is also not correct. So I think the last one, you can straight away see this is 90 degree lah. It's between the plane of the coil and the normal of the coil. Plane and normal, of course, 90 degree. So this one is definitely a wrong. So our answer is A. Okay, this one is quite basic. You have to determine the direction of area vector. It's always perpendicular to the plane of the coil. So the plane of the coil has two sides. You can say the normal to be here. You can say the normal to be there. So area vector, you pick any side, also correct. Okay, because when you do your cos theta, you just get another negative sign only. Okay, but don't worry about that. You look at the angle over here, you see which one will be the right one. Okay, just like how I analyzed it just now. Next question. A magnet is positioned with its north pole at the center of the coil. So if you look at the diagram, the north pole is not at the center of this coil over here. I think all of them have the same situation. The north pole is always at the center of this coil over here. Okay, center of the coil. Which movement of the coil will not produce an induced EMF in the coil? Okay, so to induce an EMF, we know from Faraday's law that you need a time rate of change of magnetic flux. So to induce an EMF, you need to have change of magnetic flux. Okay, to create a change of magnetic flux, you can either change, because you know that phi is equals to BA cos theta, you need to change either B or A or theta. Okay, so you have to make sure either one of these is changed. Only you are able to cause a change in magnetic flux. Only you are able to induce an EMF. That's what we want to check. So we can see here, this is the bar magnet. If we try to draw the magnetic field lines for this bar magnet, it will be something like this. Okay, apologize for the poor drawing. Okay, so when you pull your coil downwards, then that means you're pulling it away from the bar magnet. Okay, I should draw it on the side over here, but never mind, you can imagine, right? I think if you can imagine the coil here, if you pull it down, but you keep the bar magnet at the original position, you're taking away the coil from the bar magnet. So you are getting away from the bar magnet, and that means you are experiencing a decrease in the area experiencing the magnetic field. Or you can think of it as decrease in the magnetic field experienced by passing through the coil. Okay, either way of thinking is fine. But if you pull it very, very far away, then eventually the area experiencing the magnetic field be equals to 0, right? So you are changing the A, or you can think of it as you are changing a B, so therefore you are changing a phi, therefore you are inducing an EMF. So there is induced EMF in this A situation, so this is not the right answer. We will not produce an induced EMF. Okay, second situation over here, if you rotate the coil about its axis, means by you are keeping the axis along the bar magnet, okay, and you're rotating the coil just like this. You're rotating the coil just like this, where your bar magnet is like this. Okay, so you're rotating the coil like this. So when you rotate, right, you're not taking it further away from the bar magnet. You're keeping it at the same position, just rotating the circular coil over here. So you are not changing the B. Okay, you're not making the magnetic field larger. You're not making the magnetic field stronger. You're not making it weaker. You're keeping the same bar magnet, so the B is not changed. The area that is experiencing a magnetic field, well, you're not taking it further away. You're not taking it nearer, so the area that is experiencing the magnetic field should be the same. And this theta here is actually the orientation of the coil, whether the coil, the angle between B and A change or not. Whether the angle between B and A is changing or not. So in this case, our B is pointing like this. So this is our direction of B, and our A is normal to the coil, means like perpendicular to the coil, so you can take our direction of A to be pointing here as well. Okay, when I say this is a circular coil, you see it to be slightly slanted, right? You can think of it like this. This is the circular coil. This is your bar magnet. My bar magnet is here. My bar magnet is here. That's why my my magnetic field line is pointing into the page over here. And my area vector is perpendicular to this plane of the coil. That's why it's also pointing this way or this way. Okay, so the A and the B, right now by rotating the coil, you are not changing the direction of A, you are not changing the direction of B. So the angle between A and B remain the same. So B, A, and theta are all constant, so there is no change of phi, so there is no induced EMF. So no induced EMF, this is the answer. Okay, let's look at option C. Option C, you're moving left to right. So we are moving it left to right, means by this is your bar magnet. This is your bar magnet, and you are moving it like this. Okay, if you're moving it like this, you're moving it away, then you're moving it near. You're moving it away, you're moving it near, away, near, away. So in that case, the area that is experiencing the magnetic flux, experiencing the magnetic field will change. If it gets near to the end, then only this region here experience the magnetic field, but this region here probably not experiencing the magnetic field. So there is a change to the magnetic flux. Okay, same idea. If you look at D over here, to the left, you're pulling the coil away from the bar magnet. You're pulling it away from the bar magnet, so you should expect the area that is experiencing the magnetic field to decrease. So the A is changing, the phi is changing, therefore there is an induced EMF. So option C and option D here, there will be an induced EMF, so our answer is B. Okay, move on to the next question. Question 15. Okay. A rectangular coil of length L, so this is length L for this rectangular coil, is moved through a uniform magnetic field B at a constant speed V. Okay, so you can see here they use a dotted line here to represent the region that has uniform magnetic field. Okay, so inside this dotted line box over here, only we have uniform magnetic field. Outside this dotted line box, you see there's no uniform magnetic field. Outside here, there's also no magnetic field. So only this region here has magnetic field, and your rectangular coil of length L is going to move through this uniform magnetic field at a constant speed of v. So the whole motion here will be constant speed. Okay, so the length of the magnetic field is 3L. So this is the length of the coil on this side, but this side is 3L. Okay, so you know that the motion here is to the right. Okay, so which graph shows correctly the variation of the induced EMF with the displacement x of the side of PQ of the coil? Okay, so they are going to focus on this side PQ of the coil moving through the uniform magnetic field. The whole coil is moving through the uniform magnetic field, but they are measuring the displacement with respect to PQ. So it means by you imagine this whole coil here as a single dot that is placed on this PQ line that is moving like this. So we are not measuring with respect to the left side, we are measuring with respect to the right hand side. So the right hand side here is now at the starting point, and later you end the session when the whole coil is outside of the uniform magnetic field. So your PQ will be over here. So later when you see your graph over here, epsilon against x, right? Your x is actually like this. Okay, your x is from here to here. So this point here is x equals 0. This point here is x equals to 4L. Okay, so there'll be 1L, then there'll be 2L, there'll be 3L, 4L. So 1L is when you reach 1L, then that means you are fully inside the uniform magnetic field. Okay, when you reach 2L, then that means you're at the center of the region. When you reach 3L, that means you're starting to exit the uniform magnetic field. When you reach 4L, you have fully exit the uniform magnetic field. Okay, so I'll write this one is fully exit. Okay, so not fully exit yet. You should, the motion of PQ, we are focusing on PQ. For PQ to move from here to here, the motion here, the coil is moving out. Coil is exiting the magnetic field. Okay, for the motion of PQ from here to here, this motion here, the coil is entering the magnetic field. Okay, for the PQ to go from here to here, staying in the magnetic field. Okay, so this one is actually discussed in your lecture video already, but I'll just roughly go through it. Okay, during this portion of the journey, when the coil is entering, the area that is experiencing the magnetic field is increasing. Okay, because you see before that when PQ is over here, the whole coil is outside. So there's zero area that is experiencing the magnetic field. But as PQ is moving towards 1L, the whole coil is gradually entering the uniform magnetic field. So when it's gradually entering, the area that is experiencing the magnetic field will increase until PQ reach 1L, then the whole coil will be experiencing the magnetic field. Okay, remember before that the area experiencing the magnetic field is 0, but once the PQ reach 1L, then the area experiencing a magnetic field, it's the maximum area already. Okay, followed by this section of the journey over here. This section of the journey, coil is staying in the B field. Okay, not entering, not exiting, just staying in the B field. Even though it's moving, but the whole coil is experiencing the magnetic field all the time. It's not like suddenly you have an area that is not experiencing magnetic field. It's not like suddenly you increase the area that is experiencing a magnetic field. Before that, there's this much area experiencing a magnetic field. At the end, it's also this much of area experiencing a magnetic field. Throughout the process, the area experiencing the magnetic field is constant. Okay, I should call this as dA dt is not change. dA dt is equal to 0 because A is not changing, so dA dt is equal to 0. Means like there's no change in A over time. Okay, this one that dA dt should be a positive dA dt because the area is increasing. Okay, lastly, for the last section of the journey over here, when the coil is getting out, it's gradually exiting the magnetic field. So the area that is experiencing the magnetic field will slowly decrease until it fully exits the uniform magnetic field. So when PQ reaches 4L, the coil has fully exited the magnetic field. So when it fully exits the magnetic field, then the area experiencing the magnetic field will go back down to 0. Okay, so this one, coil is exiting the magnetic field. So I'll straight away write the area decreases. So area decreases, the dA dt is negative. Okay, so right now, dA dt, I'll need to show Faraday's law first, right? I think. So nd phi over dt. So the phi can open it up, become nBA cos theta. B is not changing, it's constant because you are not making the magnetic field stronger, you are not making the magnetic field weaker. But the area you are changing, if you take it out of the magnetic field or you take it into the magnetic field, then the area is changing. The theta here is constant because you are not rotating the coil. So in this case, you can take out B cos theta. You're left with dA over dt. Okay, again, this one I will change it to 1 because the area vector is pointing into the page. The magnetic field is also pointing into the page. So the angle will be 0, cos 0 will be equals to 1. So this is the equation that you have. So from this diagram, from this situation here, we can know that if dA dt is positive, then your epsilon is negative. Okay, this one, your epsilon will be equals to 0. Then this one will be epsilon will be positive. Okay, so you can see that the journey from 1L to 3L should have 0 epsilon. 1L to 3L, 0 epsilon. So this is the answer. All this thing you see is not 0, it's not 0, it's not 0. So our answer will be C. Okay, now if you look at the situation, they say, I say initially epsilon is negative, but here the epsilon is positive. Here, I say the epsilon should be positive, but it turns out it's negative. So it's the opposite direction of what I have determined. But if you look at the question, which graph shows correctly the variation of the EMF induced in the coil with the displacement x of the side PQ of the coil? How should I say it? Why is it opposite, right? It's maybe, maybe it's because they set the area vector to be pointing out the page. Is it? Is it because they set it out of the page? Yeah, it's because they say it out of the page. If they say it out of the page, right, then the theta over here will be 180. Then you become -1. Then you cancel out the negative, negative become positive. Okay, that might be the reason. If they select the area vector to be pointing out of the page, then the area vector and the magnetic field is 180 degree. So 180 degree cos you become -1, then you cancel out the negative, become positive. Okay, I don't think this should be a thing you should concern about, because in this situation over here, the way we determine the correct answer is by saying that where is the 0. You know, this is a 0. This is not correct, then that's why we pick C as our answer. Okay, so the main message I want to tell you here is, if the coil is moving inside a uniform magnetic field, there should be no induced EMF. Unless it is entering a uniform magnetic field or is exiting a uniform magnetic field, then there will be induced EMF. But moving inside a uniform magnetic field, we are not changing the B, we are not changing the A, we are not changing the theta. So no change in magnetic flux, no induced EMF. Okay, so the answer for this question is, the answer for this question is C. Let's move on to the next question. A conductor of length L is placed on two rails that are separated by a distance of x in a uniform magnetic field B. Okay, wow, so many symbols. So this conductor here has a length of L and it's placed on two rails. There is rectangular shape over here. There's two rails over here. Then the two rails are separated by a distance of x in the uniform magnetic field of B. Okay, a resistor of resistance R is connected between the rails at one end. So you can see there's a resistor here that connects these two rails. The conductor is moved with constant speed V along the rail. So this conductor is going to move on the rail to the right. Okay, now they ask, what is the current in the resistor? Oops. Okay, let's do Faraday's law. Slightly exhausted, but let's continue. Epsilon is equals to negative d phi, capital Phi over t. This is Faraday's law. The induced EMF is a negative rate of change of the magnetic flux linkage if it's multiple turns. But in this case, there's no multiple turns. It's just two rail and one conductor. So there's no like turns, this kind of stuff. So you can immediately just change it to negative d phi, small phi over dt. So now it's no longer magnetic flux linkage, it's just magnetic flux because the n is equals to 1 over here. Okay, then we continue, then we can say this is BA cos theta. This is just a definition of magnetic flux. But in this case, you are not changing a magnetic field, you are not making the magnetic field stronger, you are not making it weaker, so B is constant. The area here is the area enclosed by the conductor. The area enclosed by the conductor, if you move it to the right, the area will be changing. Okay, if you move your conductor to here, then the area will become larger. So you are changing the area. So A is changing, you have to leave it inside the differentiation bracket. The orientation is not changing, so it's constant. You're not rotating anything. So from here, we know that to continue our derivation, you involve you taking out the B, you involve you taking out the cos theta, you're left with dA dt side. Okay, cos theta over here, again, the theta is the angle between B and A. The area is here, so the area vector will be perpendicular to the plane of the area. So it's either pointing out of the page or pointing into the page. If I take it to be pointing into the page for my area vector, then my area vector and my magnetic field will be pointing in the same direction. So this one will be 0, and therefore this one will be 1. So it becomes negative B dA dt. Okay, let's continue. So we can see that the area over here consists of this length over here multiplied by this width over here. Okay, so we can break the area to become negative B. The area change it to length multiplied by width dt. Okay, we can see that as this rod is moving forward, the area will change. But when the area change, the length here will be constant. The length is not suddenly making the rectangle become larger in this way. The length is not changing, so the area is only changing this way. The area is changing this way, that means the width is the one that is changing. But what is the length of this area over here? The length will be not the big L. Okay, you have two lengths you can choose, whether it's the big length L over here or it's a small length over here X. You can see that your area here, the length is X, not L. So that's why you have to change this L over here to become the correct symbol X. Okay, your area here, okay, this is your rod. Your area here is made of X times the width. Okay, so that's why I break it like this, but X is constant. So I can bring it out from a bracket, so it becomes negative bx. So now d omega, not d omega, dw dt, change of width against time. The width is changing because you are moving forward. So how much width change is actually equivalent to the speed over here? We have discussed this in the lecture. If our speed is 5 meter per second, then that means our width is adding 5 meter every second. Because this bar is going to move 5 meter for 1 second, then that means the width is going to increase by 5 meter per second. So the dw dt over here can be replaced by the v over here. So the equation becomes negative bxv over r. Okay, so this is epsilon over here. Okay. Hey, what am I doing? bxv, there's no r. Why do I introduce r inside there? Got too nervous. Okay. This is just normal b, this is just normal x, but this one changed to v. Okay, so you also know that the induced EMF in this loop will be like what we learned in chapter 3, be equals to IR. This one is negative. I don't think they want the negative. They don't want to care about the direction. They just want everything magnitude. So you don't need to care about the sign. Okay. You can just write like this. So you don't need to introduce direction. So this is just BXV IR. So the I will be BXV R. Okay. I do this thing because I don't want to look at the direction. Okay. Ignore direction. Okay, so BXV over R is A. Okay, so I think many students might have problem because they probably memorize the formula, then they learn that for moving conductor, the formula is BLV. So they will say BLV, then they will sub in BLV over here, then here will be BLV over R, then they will pick B. But you have to know that this equation here comes from the idea of changing area. So you look at where is the area that is changing, what is the fixed length over here? The fixed length here is X, not the large L over here. That's why here X will be a more appropriate length to put in. Okay, so that's it for question 17. Let's move on to the next question. A plane of coil with n turns. So this is the coil, plane of the coil. So they're showing you a coil, but they're showing you at this angle. So you can see as a straight line only. You're not able to see the coil. You're seeing it as a straight line only. But it's the coil. Okay, and this coil has n turns, each of area A, and is placed at an angle of theta in the uniform magnetic field B. And the coil is to move through a distance x in time to the dotted position shown in the figure below. Okay, so it's going to move from this place, so it's going to move to the place where it's dotted line over here. So this coil over here this is the coil. So imagine you have a magnetic field pointing to the right like this. Okay, your screen is showing a lot of right arrow. Imagine it now. A lot of right arrow pointing to the right, representing the magnetic field. And this is your coil, but it's like this. So it's moving down like this. Okay, moving down like this. Okay, remember this is not a straight line conductor. This is a plane of the coil. Okay, so what is the EMF induced in the coil? Well, again, this is Faraday's law. Okay, break it open. You know the number of turns never change, you can take it out. You are not changing the strength of the magnetic field. You are not making it stronger magnetic field. You are not making it weaker, so you can bring it out. The area of the coil, you are not changing the area of the coil. You are just moving the coil, but you're not changing the area of the coil. The whole area here has magnetic field passing through it. Okay, the whole area here has magnetic field passing through it, but you're not changing the area. So you can bring it out. Okay, the theta here should be the angle between B and A. Okay, your B is pointing to the right and your A should be pointing this direction. Okay, so this should be the thing that you substitute. So this is 90 minus theta. So that means we need to modify the equation here to be 90 minus theta. Okay, because the theta represent different things here. They already label the theta here already, so you have to do it according to this theta. Then the angle between A and B is 90 minus theta. So you have to change it. But the important thing is you are not rotating the coil. You are not changing the direction of the area vector. You are not changing the direction of the area vector. You are not changing the direction of the magnetic field. So the angle between the area vector and the magnetic field will remain constant. So if it remain constant, that means it will not change with time. So technically that means you can bring it out this as well. So there's nothing over here. That means this is constant. This is constant. This is constant. This is constant. So if everything is constant, then this nothing over here, then it become 0. 0. Okay. If you are not sure why the differentiation bracket becomes 0, right? Imagine y is equals to 8. dy dx will be equals to 0, right? Okay. Similar idea. Okay. No matter you 8 times a times b. If there's no x, right? If there's no x, then you all become 0. Okay. So in this case, the epsilon will be equal to 0. The induced EMF will be equals to 0. Again, even if this plane of coil is moving, but there is no induced EMF. Okay, not everything that moves will induce an EMF. If it's a straight line conductor moving in the magnetic field, then it might have an induced EMF. But in this case, it's a coil moving in the magnetic field. It is not entering the magnetic field. It is not exiting the magnetic field. So the area here is constant. Okay, throughout the whole journey from here to here, it does not experience an increase in the area that is experiencing magnetic field. It does not experience a decrease in the area that is experiencing magnetic field. So the A is constant. So the other thing is also constant. So everything is constant. There's no change in magnetic flux, no induced EMF, 0. That's the answer. Let's move on to the next question. A short bar magnet moves at a uniform speed along the axis of the solenoid. So this is a solenoid here, and you have a bar magnet that is moving to the left, from right to left. So a galvanometer is connected across the solenoid. So this is a galvanometer. So the galvanometer will show you the direction, it will show you the magnitude of the current. If your deflection is greater, then that means there's a greater current passing through it. If it's a weak deflection, that means it has a smaller current passing through it. If the deflection is in this direction, then that means current is flowing in this direction. If the deflection is to that direction, then that means the current is flowing in that direction. Okay, so which graph best represent the variation of the galvanometer deflection data with time? Okay, so the bar is going to move into the solenoid and it's going to exit the solenoid. So it's similar to us saying that the solenoid is going to enter the uniform magnetic field, and it's going to enter a magnetic field, then you exit the magnetic field. Okay, so in this situation, you know that because there is change, either you can say the change in B or you can say change in A, so there will be change in magnetic flux, that's why there will be induced EMF, that's why there will be induced current. Okay, the idea is like this. Okay, I need to explain too deep. Once you enter, the bar magnet enters, right? Okay, when the bar magnet is at this position, there will be a certain magnetic flux of the solenoid will be equals to a certain value. Okay, but when the bar magnet is over here, then the magnetic flux at this position should be similar to the value earlier. Okay, end to end they should have similar value when they are at the center, and when they are at this position they have the same value, this position have the same value of magnetic flux. Okay, the idea that I'm trying to say here is if the bar is near the center over here, the motion near the center over here, you should expect the whole bar, the whole solenoid to experience the magnetic field. Okay, so when the bar is near the center, right, the whole solenoid is experiencing a magnetic field. So even though the bar is moving to the left a little bit, the whole solenoid is still experiencing a magnetic field. So there is no change in magnetic flux when the bar magnet is near the middle. Okay, because it moves slightly to the left, the whole solenoid is still experiencing a magnetic field. It moves slightly to the right, the whole solenoid is still experiencing a magnetic field. So the A never changed, the B never changed, the theta never changed. So therefore no change in magnetic flux, no induced EMF, no induced current. So you should expect to see middle here should be equal to 0. So this is no, this is no, this is not. This will be the answer. Okay, so this part, when the bar magnet is entering the solenoid, it is as if the solenoid is entering the magnetic field. So the area that is experiencing a magnetic flux will increase. So dA dt is positive. Okay, so when it's near the middle, the solenoid is staying in the magnetic field. So in this region, you can say the dA dt will be near 0. So when you're at this region, it is the solenoid leaving the B field. So in this case, you can say the dA dt is negative. Okay, so you should expect the EMF over here and the EMF over here to be opposite sign, because one the dA dt is positive, one the dA dt is negative. So opposite sign, and that's why you see one is pointing positive, one is negative. So A is the answer. Okay, but it's very rough. I'm not very specific with the sign whether it's positive or negative, but this is how I work through it. I know the center over here, the induced EMF will be equal to 0 because the solenoid is staying in the magnetic field. Even if the solenoid is moving, the whole solenoid is still remaining in the region of magnetic field. That's why A never change, magnetic flux never change, no induced EMF at the middle period of time over here. Okay, that's how I solve this question. Let's move on to the next one. An aircraft of length L, wingspan x, flies horizontal at a speed from north to south in a region where the Earth's magnetic field B is inclined at an angle of theta to the horizontal. Wow, this is a long sentence. Okay, you can imagine the situation like this. I'll draw a few different diagrams. If you look at the top view, then this is how the flag should probably looks like. Okay, so the length is L. This is an aircraft of length L. Then the wingspan is X. Wing is over here. I hope you are able to understand my diagram. Okay, so it's moving horizontal. When you say it's moving horizontal, that means if I look from the side, then this is how the plane should look like. Okay, it's moving at the speed of v. Then they are moving from south to north. Okay, so if this is an Earth, right? Then this is the north pole of the Earth, this is the south pole of the Earth. So it's moving in this direction. Okay, so now they are in a region where the Earth's magnetic field B is inclined at an angle theta to the horizontal. Okay, this is the Earth. So this is the surface of the Earth. So this is the horizontal of the plate. So now they say the magnetic field is an angle theta to the horizontal. That means by you draw the magnetic field, you probably draw it at an angle. How should I draw it at an angle? You can think of a situation like this. How should I draw it? How should I draw it? Let's say, okay, I'm turning the whole Earth. Let's say the north is near here, south is near here. So if you draw your magnetic field lines, you'll be pointing out, be pointing out, be pointing out, be pointing at an angle like this. Okay, pointing in, pointing in, pointing out. This. Okay. So now you can see that the horizontal is like this. This is the horizontal, and your magnetic field has an angle. Magnetic field has an angle of theta with respect to the horizontal. This is what they are trying to say. This is what I'm trying to draw. Okay. What is they're flying from south to north. Yeah, correct. Okay. So what is the magnitude of the EMF induced between the wingtips of the craft? So they say right now they want the EMF across the wingtip of the craft. So EMF is over here. So to imagine the situation, you can think of it as like a moving linear conductor. Okay, when the wings is swiping through the sky, it is swiping through a magnetic field. So you can think of it like a linear moving conductor. So you can think of magnetic field is pointing in this direction. So your wings is swiping through the magnetic field. Okay, so usually when we discuss this, then the area will be, this will be the imaginary area, right? Okay, so I'm going to skip some steps over here. Epsilon will be equals to negative. You are going to take out the b. You are going to so you have dA dt over here. Okay, the area over here consists of x, which is constant, and the width over here, which is changing. So you can change the area to become dx times w, where the x you can take out because it's constant. Okay, the aeroplane is not flying this direction, right? The aeroplane, of course, is flying in this direction. So this will be the direction of v. So of course your area will be here. Okay, so that's why the L is not the value that we substitute in here. It must be x. Okay, because swiping like that, it's not swiping that way. Okay, so this is wrong. Okay, so x is a constant one, then dw dt. And we know that that will transform into the speed of the aircraft. Okay, but right now, right, the b over here, oh yeah, there's a cos theta there, I forgot. I'm not in good condition. Okay, so you can take out the cos theta over here. So there is a cos theta over here. There is a cos theta over here. But be careful, I haven't finished it. This theta over here is the angle between B and A. Okay, right now our A, okay, I don't know whether you can imagine or not. This is the area. And so our area vector will be pointing, let's say, downward. Okay, then this is our B. So this is our angle. Okay, this should be the substituting in value. But the data that they give, oh, let me clear out the diagram a bit. Redraw. Okay, this is your flight. Then, as I mentioned just now, the magnetic field is at an angle. So let's draw an angle. This is the horizontal. The magnetic field is at an angle to the horizontal. So this will be theta. Okay, now your wing is swiping through an area which you can draw like this. So this is the area swiped through by the wingtip as it moves forward with V. Okay, so the area here, it's flat along the horizontal, so the area vector should be either pointing upwards or pointing downwards. So in this case, I'm going to choose it to be pointing downwards. This is the area vector. So when I say this theta here should be the angle between B and A, this should be the angle that we sub in. But they give theta to be another angle already. So you know that over here, to get this angle over here, you need to change this to become cos 90 minus theta. Okay, this one is 90 minus theta. Okay, so cos 90 minus theta. Not sure why do I want to do this, but you can do cos 90 cos theta plus sin 90 sin theta. Then cos 90 is equals to 0. Yeah, so this one will be 1. Sin 90 will be 1. Right, 1. Yes, so you get sin theta. So your answer will be sin theta. Okay, so bxv sin theta, our answer is B. Okay, why there's a negative sign here? Because they ask for magnitude. Then if you change it to magnitude only, then you don't need to introduce a sign. So just bxv sin theta. Okay, I think the main issue that many might have is to determine where is the area vector pointing. Okay, if you think of this as the area, so think like this. This is the wing. This is the wing of the aeroplane. Okay, let's say the aeroplane is like this. Aeroplane is flying horizontally like this. So the pen here is representing the wing. So the wing is swiping through horizontally. So the wing will swipe out an area like this. Okay, so this is the area. Your magnetic field is pointing at an angle to the horizontal. Your magnetic field is pointing at an angle to the horizontal. So this is the angle to the horizontal. Horizontal is here at an angle, so this is the theta. But the area vector is pointing here or pointing here. So area vector is pointing downwards. Magnetic field is pointing here. So this is the angle that you want. Not this one, this one. So it's 90 minus theta. Okay, that's why you transform, you become sine theta, then you become bxv sine theta. So this is how we get our answer over here. Make sure you don't put in L as your answer because your aeroplane is not going to the right. If your aeroplane is going to the right, then this is the one that is swiping through the magnetic field. But if you're going upwards like this, then the wing is the one that is swiping through the magnetic field. Okay, next question. The light bulb connected in series to a watt in a DC circuit will dim slightly slower when we disconnect the circuit. Okay, let's draw a DC circuit. So you have a battery, and you're going to connect it with something. Okay. Then you're going to connect it to a light bulb that is in series. Then you connect it like this. Okay. So they ask which one will dim slightly slower. Okay. Dim slightly slower is an effect of inductance or capacitance. Okay, both will show this kind of effect. Okay. But how it works is like this. You need to put an inductor inside. Okay, only you have inductance effect. Only you will make the current change slower. Okay, the idea is like this. How should I explain it? Okay, let's start like this. Disconnect the circuit. What does it mean is that the current drop from, let's say, I to 0. Okay, so drop from I to 0, then what does it cause? It causes your di dt to be negative. So if you put it into epsilon is equals to negative L di dt, okay, this is because if you have an inductor over here, then using this, you know that epsilon will be positive. Okay, so if you have current flowing this way, okay, if you have current flowing this way, then our epsilon is positive, means by you can think of it like a battery with current flowing this way. Remember, from negative terminal to positive terminal, this one is called a positive epsilon, right? So you can imagine it to become like a battery like this, connected to replace the inductor. Okay, you get a positive induced EMF, you can imagine it as if you can replace it with a battery. It's just a very short-term temporary effect. It only happens when you are disconnecting the circuit only. You can think of it as if you suddenly change the inductor, become like a battery. But the battery, as you can see, is in this direction over here. Okay, so like this. If you have a battery over here, it will pump charges from negative terminal to positive terminal. That's the function of battery, right? You want to pump charges from negative terminal to positive terminal. So when you disconnect the circuit, you are making the current drop to 0. But now you see, when you are dropping it to a 0, the inductor can suddenly function like a battery like this. And this battery is actually pumping charges from negative to positive. So if you replace the inductor with a battery that looks like this, it is as if this inductor is helping the current, helping you to pump the charges in this direction. Okay, so in other words, it is trying to oppose the decrease of current. Okay, because this battery here functions to pump charges from this side to this side. So it is as if you are trying to oppose the decrease in current by pumping the charges in the same direction of the current. Okay, so because you are trying to pump charges in the same direction of the current, then the current will not drop so fast. Initially, you drop very fast. If there's no battery over here, you drop faster, right? But now you can see, if I install a battery like this over here, you pump charges in that direction, so you make the drop not so fast. That's why you dim slightly slower. Okay, it's a very terrible explanation because now it's 2 a.m. The battery. So this battery here wants to pump charges in this direction. Okay, so if you want to pump charges to the right, that means you are opposing the decrease in current, because you know current is flowing in this direction and it's decreasing, but you try to pump it in the same direction. That means you try to oppose it from decreasing. Opposing the decrease in current. So this is just Lenz's law. Okay, so this one is just a theory for how self-inductance you make the current change slower. Before that, you should drop very fast, but because there's Lenz's law trying to oppose the decrease in current, that's why the current will not decrease so fast. So you make the light bulb dim slightly slower. Initially, it should dim very fast, but because there's an inductor there, you dim slightly slower. Okay, so the conclusion is that we should install inductor here. But fixed resistor is not an inductor. Transistor is something that we never learned before. Rheostat is something like a solenoid. I think you know, right? Rheostat looks like a solenoid, right? I should have copied a picture of a rheostat. But a rheostat looks like a solenoid, and because it looks like a solenoid should have inductance, right? We always replace the inductor symbol. The symbol for inductor is solenoid, right? So this is an inductor. An inductor is usually in the shape of a solenoid, and rheostat Rheostat is the one that allows you to change the resistance. Rheostat is a variable resistor. Okay, if you are doing Ohm's law experiment, the thing is called a rheostat. The one that you can slide along to change the resistance, to change the current, that is a rheostat. And it has the shape of a solenoid. So because it has the shape of a solenoid, it has inductive properties. Because it has inductive properties, that's why it's suitable to replace an inductor. Technically, you should put an inductor, but if you don't have an inductor, then rheostat can be a good replacement because it is in the shape of a solenoid, so it should have some inductive properties. So that's why rheostat will be the one that causes the light bulb to dim slightly slower when we disconnect the circuit. Okay, next. Large alternating current in a cable is inducing an EMF in a coil near the cable. In which range I should zoom in. Okay. Large alternating current in the cable is inducing an EMF in a small coil held near the cable. So this small coil here is held near the cable. So you are trying to put a large alternating current in this cable. So in this cable, the current is flowing to the left, to the right, to the left, to the right, keep on changing direction. So because it's keep on changing direction, the current is changing. So if the current is changing, the magnetic field that is produced by the current is changing. So the magnetic field that is passing through the coil will be changing. So the magnetic flux of the coil will be changing, and therefore there will be an induced EMF in the coil. Okay? So they ask in which arrangement of the coil and the cable is the EMF induced in the coil the maximum. Okay, so let me write down the sequence. So changing current, in cable is going to cause changing magnetic field produced by the cable. So the changing magnetic field by the cable will cause the magnetic field through the coil to change. Magnetic field passing through the coil changes. So there will be change in magnetic flux of the coil. Therefore, it will cause an induced EMF in the coil. Okay, so this is a straight wire. This is a straight line cable, a very long straight cable. So you expect the magnetic field to be produced by this cable to be perpendicular. The plane should be perpendicular, so it should look something like this. Okay, we learned this in chapter 4, magnetism. So if the current is flowing in this way, then your magnetic field will be up, like this, like this. Okay, but it's an alternating current, means by the current will change direction. So later when the current flows in this direction, then your magnetic field will be changing direction. Okay, so the magnetic field constantly change from clockwise to anti-clockwise, clockwise to anti-clockwise, clockwise to anti-clockwise. So because there's changing magnetic field, then the magnetic field passing through the coil will change. Okay, so let's analyze how does the magnetic field passing through the coil changes. Okay, so in the first situation here, if we place our coil like this, then what you will see is when the current is flowing to the left, the magnetic field is pointing into the coil in this side, but at the other side it's pointing out the pitch. Okay, you can look at it, the 3D version is pointing up, so this one is pointing out of the page, this one is pointing down, so this one is pointing into the page. Then once the alternating current change to another side, then it become, this side will become dot, then another side will become cross. Okay, so you can see it's half of the area with magnetic field pointing in one direction, half of the area with magnetic field pointing in the opposite direction. So you should expect that it's equivalent to, like, if you calculate the whole magnetic flux, it should be equal to 0. Because half of the area is pointing this way, half of the area is pointing this way. So one of them is cos 0 degree, one of them is cos 180 degree. So half of it will be a positive magnetic flux, half of it will be a negative magnetic flux, but they have equal values, so you add them up, it becomes 0 at the end. So for this arrangement over here, if you place your coil like this, the magnetic flux will be 0. No matter how many times you switch the current direction, the magnetic flux will stay as 0 all the time. Because half of it has a positive magnetic flux, then half of it will be a negative magnetic flux. Then you add them all up, you enter back to 0. So this one is not the one that you should have to get an induced EMF, because the magnetic flux always stays at 0. Okay, if you use the arrangement in B, okay, based on what we see over here, when at certain times your magnetic field will be here dot, then here will be cross. Okay, so at certain time the cross inside, it's all crosses in the circular coil over here. Okay, but if your current change direction, then of course here will become crosses, and then here will become dot. Okay, I hope you get the idea. But here we change to become dot. Okay, so the whole coil here is experiencing the same type of magnetic field. They are all pointing in the same direction. If they are pointing into the page, they all point into the page. If they are pointing out of the page, they all point out of the page. It's not like the situation in A anymore. Situation in A, half of it is up, half of it is out of the page, half of it is into the page. But now they are all either out of the page or into the page. In this case, the magnetic flux will not cancel to 0. In this case, there will be change in magnetic flux when you go from out of the page to into the page, out of the page to into the page. The magnetic flux keep changing. So you induce an EMF in the situation over here because the magnetic flux is changing. Okay, you move to situation C. Situation C, you place your coil. If this is your cable, right, you place your coil like this. Okay, you can see like this. This is your cable. You place your coil like this. Okay, you know that your magnetic field is also parallel to your coil. Your magnetic field will be parallel to your coil. So in this case, your coil is like this, but your magnetic field is also like this. So there will be no magnetic field passing through the coil. Okay, again, your coil is like this, and the magnetic field lines is also like this. It's getting larger. The magnetic field lines, they are parallel to each other. So you see no magnetic field passing through the coil. So no magnetic field passing through the coil. That's why you can say that the B and the A are 90 degrees. Okay, the area vector is pointing in this direction, but the magnetic field is pointing in this direction. So the theta is equals to 90 degrees. So cos 90 degrees will be equals to 0. That's why phi equals to BA cos theta will equals to 0. Okay, so all this one, even if you change the magnetic field, change it from clockwise, anti-clockwise, clockwise, anti-clockwise, because the area vector and your magnetic field are right angle to each other, that's why the cos theta will be equals to 0. That's why magnetic flux will always stays at 0. because the magnetic field never pass through the coil. The magnetic field is parallel, same plane with the coil, not passing through the coil. So no magnetic flux, no change in magnetic flux. Okay, the situation in D is also similar. It's also because there's no magnetic field passing through the coil. Okay, you have to, if this is your cable, your coil have to be like this. You have to put it like this, only there's magnetic field passing through it. In this case, all the magnetic field will be passing through in the same direction. If you put it like this, half of it will be into the page, half of it will be out of the page if you place it like this. If you place it like this, then it's parallel, no magnetic field will pass through it. Okay, so the answer here will be B. Okay, because you want maximum induced EMF. This one it will be phi equals 0, this will be equals to phi equals 0, this one also phi equals 0. Cancel out. Okay, magnetic field lines are in the plane parallel to the area of the plane of the area of the coil. Okay, and when that's the situation, no magnetic field passing through the coil. Okay, so that's it for this question. Let's move on to the next one. Question 24. You have a coil spinning in a magnetic field. Which of the following causes an increase in the induced EMF in the coil? Okay, so I'm not going to draw a diagram. Induced EMF for rotating coil, you know that it's NBA omega sine omega t. Okay, so if you want to increase the induced EMF, you can either increase the number of turns, increase the magnetic field passing through the coil, increase the area of the coil, or making it rotating faster. This one won't, this one is irrelevant. This one, it depends on time. Okay, so spinning the coil faster means by you are increasing the omega. Of course, increase the omega will cause increase in the induced EMF. Keeping the flux at the constant rate means by keep the flux at a constant rate. So means by you're not changing the flux. No? If you're not changing the flux, keep the change of flux at a constant rate. That means d phi dt is constant. D phi dt is constant won't help you to increase phi. Your EMF will be constant. Keep the change of flux. Okay, d phi dt is constant, then your phi will be constant. You will not increase your induced EMF. Okay, shrink the size of the coil. A decrease, you definitely cause epsilon to decrease. This is stated over here. Decrease the number of turns, of course, it will cause your epsilon to decrease. So the answer is A. Okay, next question. Which of the following action will cause the induced EMF to be in the direction of the current flowing through the inductor? Okay, so if you have an inductor today, and you have current flowing through it, how should you change your current? Only your induced EMF is in this direction. Okay, so if your induced EMF to be in the direction of the current flowing through an inductor, so you want your induced EMF over here to be in the same direction as the current over here. Okay, so it is as if you change it to like a battery that pumps from negative to positive, right? Battery always pumps from battery always want to pump from negative to positive. So under what kind of situation will your EMF be pointing in this direction? Okay, you know the direction of the EMF always want to oppose the change in magnetic flux. Okay, oppose the change in magnetic flux means by they want to oppose the change in magnetic field. That means they want to oppose the change in the current. Okay, so if the current is flowing in this direction and yet you still want to pump in the same direction, then that means you are opposing it from decreasing, right? It's because the current is decreasing, you want to oppose the decrease in current, only you pump it in the same direction, right? Okay, if your current is increasing and you want to oppose the increase, then that means you want to pump in the opposite direction to try to decrease, to try to make the increment slower. Okay, again, if your current is flowing in this direction and the current is decreasing, your induced EMF will try to oppose this decrease in current. So that means it try to increase back the current. If you want to try to increase back the current, you try to pump in this direction. Then that's why your EMF is in this direction. That's why the answer should be decrease the current. Okay, so let's try another scenario. What if your current is increasing? Your current is increasing, then your EMF will try to oppose the increase in current. So you want to try to decrease the current. If you want to try to decrease the current, then you want to pump in the opposite direction. That's why your induced EMF will be in the opposite direction of the current. Okay, so these are two common examples of how to think about the direction of the induced EMF. For this situation, you want to decrease the current flowing in the inductor. Decrease the current flowing in the inductor is going to decrease the magnetic field in the inductor. Therefore, it's going to decrease the magnetic flux of the inductor. Decrease the magnetic flux linkage of the inductor. Okay, so then therefore you have induced EMF. Okay, so this EMF here will try to increase back the magnetic flux of the inductor. So you try to increase back the magnetic field in the inductor. So you try to increase back the current flowing in the inductor. That's why you pump in the same direction as the current to try to pump back the current that is dropping. Okay, that's Lenz's law lah. So that's it for this question. Let's move on to the next one. A magnetic field exerts a force on the charged particle always, or is it not always? Okay, so the idea is like this. I'm going to go through it quite fast. F is equals to Q V B. Okay, so the question is for F to be not equals to 0, means by if you want to exert force, what must happen? Your Q must not be equal to 0. Your V must not be equal to 0. Your B must not be equal to 0. Only your F cannot be equal to 0. Okay, but there's also one thing. Your V cross B cannot be equal to 0. Only your force cannot be equal to 0. So that means theta should be not equal to 0. Okay, if your theta is equal to 0, if theta is equal to 0, then V cross B will be equal to 0. Okay, let me break it open. It's VB sine theta must not be equal to 0. Only F will not be equal to 0. Okay, So that means by theta cannot be equal to 0 degree. Because theta is 0 degree, then sine theta will be 0, then your f will be 0. So you have to make sure the theta is not equal to 0 in order to have magnetic field exert the force. So theta is equal to 0 if v and b are in the same direction. So that means by your particle cannot be moving along the direction of magnetic field lines. Okay? Okay, so you cannot have your particle move along the magnetic field line. If you move along the magnetic field line, then the v and the b will have the same direction. So theta will be equal to 0, sine theta will be equal to 0, then the f will be equal to 0. So C is definitely wrong. Okay, so if we know C is wrong, then we know it's not always anymore. So A is wrong. Okay, so as long as the particle is not stationary, will be wrong already. Because you know that if it moves along the magnetic field lines, it will not have a force. And you know that when it moves along the magnetic field line, it is not stationary anymore. Okay, so it doesn't, so what I'm trying to say here is if the charge particle is moving, doesn't mean it must have a force. Okay, because this is what D say. A magnetic field exerts a force on the charged particle as long as the particle is not stationary. No, even if the particle is not stationary, the magnetic field can exert zero force on the charged particle too. It's when the particle is moving along the magnetic field lines. So all three of this is wrong. That's why the answer is B. Okay, let's move on to the next question. The galvanometer connected to a solenoid is experiencing a deflection to the left. So you can see they already label for you the direction of the current, and they already show you the deflection is to the left because your current is flowing from right to left. Okay, so what might be happening? Okay, so how do I do this thing is, let's try to determine the north pole and south pole for this solenoid first. So if you use your right hand grip rule, you will see that your thumb will be pointing to the right. Yeah, your thumb will be pointing to the right. Okay, if you want to draw the situation, so bad. Okay. Okay, your thumb will be pointing to the right. Therefore, you know that this is a north pole, this is a south pole. So you see this is a north and a south, therefore you know that they are trying to attract each other. So the attraction here is trying to oppose something. So what is it trying to oppose? Trying to oppose it from being far apart. Opposing it from moving away from each other. Okay, so what is happening right now? The bar magnet is moving away from the solenoid. Only the solenoid will try to attract it back. Or the solenoid is moving to the right. Then the solenoid will try to create attraction to pull itself back to the left. Okay, they are moving far apart. That's why they want to attract each other. Because the induced current always want to oppose it from happening. So what is causing this induced current? What is causing this induced current is them being moving far apart. So we'll try to oppose them from moving far apart. That's why they want to attract each other. Okay, so if you see getting away from the solenoid, that is correct. If it's getting near, then it's no. If it's getting near, then it's no. Okay, it's only because you move away. So only that they will create induced current to try to attract it back. Okay, so this one is Lenz's law. Lenz's law want to attract it back because you are moving away. Okay, so what is happening to induce a current? It's the bar magnet moving away to the left. Okay, the idea is bar magnet move to left. So it will cause the magnetic field passing through the solenoid to decrease. Magnetic field passing through solenoid decrease, then therefore the magnetic flux linkage of solenoid decrease. Therefore, there's an induced EMF. Because this is a closed circuit, you induce a current. And because there's an induced current in the solenoid will cause a magnetic field produced by the current in the solenoid. Okay, so the bar magnet will interact with the magnetic field produced by the solenoid. The solenoid will interact with the magnetic field created by the bar magnet. Therefore, they will exert a magnetic force on each other. Okay, so once again, this whole part here is the effect. This whole part here is the cause. Okay, so the magnetic force, you try to oppose the bar magnet from moving to the left. So by how to oppose the bar magnet from moving to the left is by exerting a force on the bar magnet pointing to the right. How to oppose? Exert a force to the right on the bar magnet. So how do you exert a force on the bar magnet which is pointing to the right? By having an attraction. Okay, because you know this is the attraction, therefore you know that south is on the left, north is on the right. Then from there you know what kind of magnetic field you need. Then from there you know the induced current will be in what direction. You know the direction of the induced EMF. Okay, so this is just trying to tell you how the whole thing works. Okay, so that's it for question 28, and I believe that's the last question for chapter 5 revision quiz. I'm sorry that I've done this in a rush and in one go, so there are some questions that I didn't manage to explain really well. So if you have any questions, feel free to just follow up with me. You can comment under the video, or you can just ask me through Telegram or whatever. Okay, once again, sorry, sincerely apologize if I mess up the explanation of certain questions. If you have any questions, just feel free to ask me when I'm in a more sober state. Then yeah, I might give you a better explanation by that time. Okay, but that's it for chapter 5 revision quiz.